We're going to go back to the 18th century. And Antoine Lavoisier, he is known as the father of modern chemistry. He actually named the element oxygen, interesting enough. He wasn't the first to discover oxygen, but he understood how it worked in water. And he was really fascinated by combustion and how oxygen was used in combustion, and the fuel of combustion produced off-gases, but everything was conserved. It's a conservation of matter. So he's very focused on that. And he theorized that combustion of, like a fire, was similar to respiration, that each of us are an engine by itself, and we're all combusting. And he's right there. And so we're breathing in oxygen and releasing CO2. We're eating food. We're releasing food. And we have water vapor and a lot of things going on. So we are, we're walking around as engines. And CO2 is a byproduct of that process. So he worked very diligently. He actually was a tax collector. He was born into a tax collector family. He went to school as a lawyer, but he was really fascinated by science. And so he was very focused on this respiration thing and looking at the heat generation from not only combustion but in CO2. So he built some contraptions that nobody else has ever done before, where he was actually measuring the respiration of people under sitting conditions, under activity. And he worked very closely with his wife. She actually did the artwork. She actually did all the paperwork. She actually translated other people's research from other languages into French. So it's pretty amazing that was done. And Lavoisier, he theorized that the CO2 we're respirating was filling up the room and displacing oxygen and making the air bad. Unfortunately, his studies in indoor air quality and chemistry were kind of cut short by the French Revolution. And unfortunately, his head was also cut off during the French Revolution. Another scientist once said, so quickly his head was lost, there may be not another one like it in another 100 years. So on that, let's move forward another 100 years. We're moving to Germany now, and Dr. Pettenkofer, he was well known because he understood the relationship between bad water and cholera. Cholera is a bacteria that grows in water, and it's like a pandemic, okay? So it spread really bad, people were dying all over the place. And he realized that clean water and the disposal of sewage was necessary. And he taught people all over the world. People would come to Bavaria to learn about this stuff. But he also took it to personal hygiene. He also took it to air. He was focused on air in the space. And he was trying to figure out how the air was working in the space. And he actually said that, Anton was a little bit wrong. The CO2 is not displacing the oxygen, but the CO2 is building up the space. There's still plenty of oxygen in the space to breathe and keep you healthy. But the CO2 he was measuring up to 5.5% or 5,000 parts per million. So he actually set a figure to say, hey, this is a good value for indoor air. And that was 0.1% or 1,000 parts per million. How about that? He also, was focused on, because he was focused on hygiene, he was focused on health. He wanted to know how the diet affected this respiration process. So he built another contraption. We actually put people in a box, fed them different foods, had them do different things, and saw what the respiration was. Today's known the respiration quotient. And so he did that, and we discovered a lot. So a lot of the science up into the 20th century was based on what he did. And we're going to move forward to the 20th century, early 20th century. And we have Professor Yaglo. He was a doctor in Boston. And he was actually hired by ASHRAE, which is the American Society of Heating and Ventilation Engineers, which is the predecessor to ASHRAE. And he was looking at ventilation, and he was looking at odor. Why? Because at the time, the ventilation rates were really high. There was a gentleman named Billings in the 1890s that did heating and ventilation. He says, well, the ventilation rate should be 30 CFM per person to create a healthy indoor space. And as we started to develop more heating systems, air conditioning systems came about, and we were ventilating more mechanical systems, it's like, wow, we're spending an awful lot of energy reheating and tempering this air. Sounds familiar, doesn't it? And so he was looking at this, and so the real focus was, okay, what does the ventilation should be to make the room comfortable? And by comfortable, we're talking about odor, not any other contaminants, but we're focused on odor. So he was looking at odors of people, and he was trying to correlate, what can I correlate with the odor? And he was trying to correlate the CO2 with the odor. But he couldn't find a direct correlation with the CO2. But of course, back in his time, people didn't shower as much as we do today, right? A shower wasn't a daily thing. Maybe it was a weekly thing. It depends on your social status as well. And there wasn't any antiperspirant, so there's a lot of challenges back there. But he was unable to do that. But he did determine, what was acceptable to people as far as odor was concerned. And how he did is because you had people sniffing, olfactory. Our nose is one of the most powerful instruments in the world. It can really detect things very quickly and very easily. The other interesting thing is our nose also gets used to things very quickly as well. So we can't smell our own body odor after a period of time. Or if you go into a conference room that has a lot of odor in it, you get used to it. But people that first walk in, they're the ones that could do it like this. So that's what we're focused on there. So he looked at that. He was measuring. He had this chamber. They like building chambers, don't they? Sticking people in the chambers. Had people going up and smelling after different people went in, changing the ventilation rate, looking at CO2, and he was actually using CO2 as a tracer gas. So as the CO2 was leaving the space, he can determine what the ventilation rate was based on the CO2. So that pretty much changed the ventilation rates thereafter for the HVAC people. And in 1973, ASHRAE came out with the first ventilation standard, 62/1973. And I'm just going to touch upon that. So one of the key things, why do we build buildings? We build buildings for the people to work in them, to occupy them, to live in them. So we are focused on creating an environment for the people. And so we want to ventilate for the people. And we want to make sure that the air that's coming into this space is clean. That we are removing any contaminants, displacing the CO2 that's in the building up in the space, and creating a healthier space and a less odorous space. In 1981 was the next revision, and there was also a revision of the title. Interesting thing happened in 1981. It was after the energy crisis of the 70s, and ventilation rates went way down. I'm not going to discuss that specifically, but it was a key thing that changed things in the future. But the topic about carbon dioxide came out more and more during the development of 62, and that's why I'm addressing it. So here we're talking about carbon dioxide. We're talking about how you're consuming food. So it's basically going back to what Anton did back in the 18th century. And, to recognize that relationship between CO2 and ventilation. I want you to focus on this number down the bottom, that 0.03%. Okay, that's the outside air CO2 value, or 300 parts per million. So they figured, if you have 300 parts per million outside and you have approximately 15 CFM of air, and everybody's seated in the room like you are now and not really doing anything, then it would maintain about 1,000 parts per million inside. There's that magic number again. Moving on to 1989, and it started to develop further. Started really discussing CO2 and carbon reduction and the effect on the diet and odor. So this goes back to both what Jagela was doing and what Pettenkofer was doing. And they very clearly mentioned 1,000 parts per million. Again, that's for people sedentary, sitting down, not doing too much exercise. And they very clearly stated that, hey, CO2 is not a contaminant. This value of 1,000 is not for, you're going to get sick if it's higher or not. 62 is not a safety code. It's a comfort code. It's an indoor air quality code standard. So 19 further added this Appendix D, and this Appendix D showed this relationship between the oxygen consumption and the CO2 generation. And it had this respiration quotient in, and basically, on the y-axis is actually liters, and not CFM, liters per second, and that's what the 0.3 value is. So basically, if you're sitting, staying still, your metabolic rate is just over 1, and your CO2 generation rate is 0.3. Well, of course, we all have heard about carbon buildup in the atmosphere. The CO2 value has significantly changed outside since we started talking about CO2 in the 60s and early 70s. And this chart represents this, that we have the CO2 being measured in Hawaii on a regular basis. The black line represents the mean. The red line means that the CO2 changes with the seasons, but it continually goes up. So if we look at this formula, and we look at today, it's actually around 420 as an average. And if we take the existing value of 0.3 and we substitute that in, we actually have an airflow rate that is much higher. We went from 15 to 18 to maintain that same 1,000 parts per million. Have to be aware of that. It takes more ventilation to move out the CO2. The differential has changed. So I also want to take a look at the ventilation tables from 1989 to current day. So back in 1989, the ventilation was pretty much just focused on per person ventilation for any space that was occupied. For spaces that weren't occupied, then it was ventilation per square foot. However, that changed with Addendum N 2001, and that ended up in the 2004 62.1 version, and it was adopted into mechanical codes thereafter. And the ventilation requirements have then broken up into ventilation per person and ventilation per square foot. So, because it recognized, there's plenty of things in the building that are contributing to bad indoor air quality. You have a lot more printers, you have a lot more copy machines, just the materials that things are made out of, clothing that we wear, everything is contributing to bad potential added VOCs that are in the air. So we ventilate for the space, even if the space is unoccupied in the current standards. But I also want to take a look at the ventilation rates and how they've changed. And I can't read what this is. Okay, that's the dining room. So the dining room, it used to be 20, and now 10 CFM. So the ventilation rates have dropped. Okay, and this is the office space. In the office space, also 20 and 17. And in the conference space, 20, but now 5. Very significantly different. So we are ventilating the spaces even less than we were before. We can expect that the CO2 values in the spaces are going to be much higher. There's a relationship between ventilation and CO2 values. And I'm going to go further with that. So that's a reduction in ventilation that has happened between 1989, when we first talked about DCV, and first talked about using CO2 as a measurement, to now. A lot of people think this CO2 sensor thing is magic. If I put a CO2 sensor on the wall, I'm automatically maintaining good indoor air quality. Well, if you attended any of the earlier sessions in this room, you would see that, no, CO2 is just one of the many things you should be looking at as far as the room. You have particulate matter, you have VOCs, there's many other things you should be looking at. It doesn't automatically make good indoor air quality. It's an indicator. It's not a direct measurement. We're trying to determine how many people are in the space. We're trying to count the people so we can ventilate for the people, because we have a ventilation rate per person. It's not measuring the ventilation rate directly. It doesn't identify the source here. So buildings, you're all practitioners in this room, which is great. I'm not talking to consulting engineers, I'm talking to people that actually have to make buildings work. So we know that buildings are very complex. They're like human beings. You can do something one part of the building, it affects the other part of the building. And so you can actually have spaces that are more negative than others. Not on purpose, but by accident, because things aren't functioning the way they exactly should. You could actually be drawing through the envelope. You can be drawing from a crawl space that maybe has radon in it. You may be drawing from a janitor closet that has chemicals stored in it. A CO2 sensor is not going to detect that. It's just going to tell you that, hey, you're taken from a space that has less CO2, so the CO2 value is going down, but the air quality may not necessarily be good. It's also dependent on many correct assumptions. Each one of us is like a thumbprint. We all generate CO2 at a different amount. We have different diets. We have different metabolisms. And it's also dependent upon pressure and temperature. It's a gas. Follows Boyle's gas law. And so if you are in Denver, for example, you have to make an adjustment to the sensor itself so it detects correctly. A lot of people don't know that. They just slap the sensor on the wall, then they make adjustment. It's reading it correctly. Degradation and drift. The way the CO2 sensor works is it has a beam of light in there, and it's measuring the gas, and that light bulb can degrade. It can get dirty. There's usually background calibrations and these things. They're assuming they're background calibrating to an existing 400 ppm. So just that background calibration causes drift over time. So these things do have to be calibrated. It's going to happen. Okay, so as I said, it's a complex relationship. It's a mass balance relationship. We're looking at a CO2 coming from outside of a space into a space. We have something in the space generating more CO2, that's us, the people, and then we have the CO2 leaving the space. And that relationship is all dependent upon the ventilation rate, the number of people, and the generation that they are producing the CO2. And that's what makes it complex. But through this, you can do the math, and you can actually kind of figure out what that CFM per person rate is. But unless you know exactly, it's hard. You can't put a mask on every single one like Lavoisier did and measure their CO2. You're making assumptions. You're making a guess of what it is based on known parameters. So if I said to you, it's 1,000 parts per million in this room right now, can anyone tell me what the ventilation rate is? You can't, because you don't have enough information. There's too many unknowns. You have to know the number of people. You have to know what the people are doing, what the generation rate is. Then maybe you can tell me what the ventilation rate is. There's a gentleman named Dr. Andy Pursley. He's been very much involved in ASHRAE for 3 decades, maybe 4. And he works for NIST. He wrote a new paper. He's been focused on the built environments for a long time, ventilation, leakages in building infiltration, CO2. He's known as the expert in CO2. So he wrote this paper about 5 years ago about a new way to, maybe a little bit longer than that, 6 years ago, to determine, calculate CO2. Because the method that we had in '62 all the way up into 2019 was that same chart that was in 1989. So it was outdated. So in 62.1, we worked on creating a new method, and based on what Andy did, what his research did. So I'm just going to walk you through it so you get a better understanding of how you determine ventilation and the generation rate from CO2. So you have this respiration quotient, okay? This is, again, the conversion of oxygen to CO2. And this conversion, again, is dependent upon your diet. So a Japanese respiration quotient is going to be different than an African's respiration quotient, different than a North American's respiration quotient. A vegan versus a carnivore is going to be different respiration quotient. But we're going to assume that most people, the average diet in North America is 0.85. And that's what it is in this formula. The basal metabolic rate, that's the energy that our body uses to stay alive. It's the base energy that we need to function, to keep our brains going, to keep our heart going, to stay basis. So that's the base function. Then we have this metabolic rate, and this metabolic really has a big impact of the CO2 generation. It's a really key thing, and there's a chart here to the right that shows that metabolic rate. It's different. If I'm doing this right now, I just increase my metabolic rate. If I act like a slug, then it's quite low. Again, I mentioned temperature and pressure. Yes, CO2 is affected by temperature and pressure, so you have to adjust. Are you at sea level or are you not at sea level? Are you at room temperature or is it freezing? So let's take an example of a middle school classroom, okay? And I'm going to take example all boys middle school classroom because women generate CO2 at a different rate than men. So just for calculation purposes, it's easier to use one value. So these are the numbers for a student. You got the respiration quotient, you have their generation rate, you have their metabolic rate because they're just sitting at the desk not doing much, and they're not running around right now. And then you calculate that out, and you get this generation rate for these tween children. And then you take that, and you look at ASHRAE Standard 62 or the mechanical codes, and you have 10 CFM per person in a classroom, 0.12 CFM per square foot, and 35 people per 1,000 square foot. Those are default values in the standard. Do the math, 10 times 35, 0.12 times 1,000, and there's our minimum ventilation rate, 470 CFM or 13.4 CFM per person. Plug that in the formula, and we come up with 1,129 ppm. That's pretty much for all boys middle school age. So what happens when these boys go to the gymnasium and they start running around? So we'll switch that up. Well, in a gymnasium, you're going to have a higher metabolic rate. We're going to move that up, 3.8. You're generating more CO2 because you're moving around. That changes the generation rate, and the steady state, it's almost doubled. 2495. Both of these are correct. Both of these meet the ventilation requirements, but they're different values. Okay, so you have to know where you are, where you're using the CO2, what people are doing to correctly use the CO2 sensor to understand. It's not a one number fits all. It's not 1,000 fits all. So in 62, we're on our 5th iteration. ASHRAE standards are consensus standards. They're ANSI. We go out, we get people to reply, comment, and we improve. And initially, the first revision basically showed, hey, engineer, here's all the formulas, make the calculations. And people are like, whoa, I can't do that. That's too much work. And I really don't think it is. You could do spreadsheets, you could have software to do it, but we listened, we tried to work, and so we came up with maybe a quicker solution. And there was questions that, hey, code officials wouldn't know what the right value is if it wasn't calculated for them. So we're creating this table, and this latest version, the 5th version, is out right now. So if you want to download it from the ASHRAE website, for the review website, you can do that and take a look at it. It's available until June 12th. If you comment on it, I'm going to have to do more work, and I'm going to be frustrated. But please, it's all right. That's the process. It's only been 5 years. So these tables are built, basically show the differential CO2 value. So if you can assume the outdoor CO2 is 400, you can assume it's 420, and then you add this differential value to it. But this is the default. And what's the important thing is default is, again, you have to understand that we have in ASHRAE 62, we have a default occupancy, a default square area, and if the default occupancy ratio is not the same, then you have to adjust for that. And we put formulas in the standard. It is mandatory to make that adjustment. Otherwise, you're going to have a completely different value, and you're not going to be using your DCV correctly or understanding what the indoor value should be at steady state. So I just highlighted a couple spaces in this table, 2520 for the music and theater and dance, 2200 for auditorium. Try to remember these numbers as we move forward because they're going to come up again. Again, these are much higher than 1,000 parts per million, right? People aren't moving around. They're sitting down watching the show, but still they're higher. Some people are moving, right? Maybe the people on the stage are moving, but the people in the auditorium are just sitting there. It's because the ventilation rate is lower for those spaces. Sensor placement. It's an important thing. This is a fairly large room. Where would you put the CO2 sensor in this space? The best place for a CO2 sensor is actually in the breathing zones at the level your heads are where you're sitting. Some people try to put in the return duct, but if you have short circuiting, if the supply air is going directly in the return air, then you don't have a true CO2 reading. Some people try to put them in the unit, and I'm going to show you what that looks like in some cases. Pretty much, but they should be in the zone. But will one CO2 sensor work in this room? Maybe not so good. If the CO2 sensor's on that back wall over there, perhaps somebody's sitting really close to it, and they're breathing on it, and they're raising up the value, so it's not representing the true mix. So you may have more than one CO2 sensor in a space like this to get a better idea. And CO2, you know, it's not instant. We have to fill the whole volume of this room first with CO2. And at the same time we're trying to fill this volume, the assumption is we're bringing ventilation air and diluting it. So it's a slow process. Basically, it's 3 times or its inverse of the air changes. So if you have 3 air changes per hour, it pretty much takes 1 hour before you come to a true 95% steady state. So in the standard, we also recommend control requirements because there's been a lot of incorrect control requirements, which is great for energy savings, but not so good for indoor air quality. And sometimes it's the reverse. Sometimes it causes too much ventilation because you're relying on a value like 1,000, but the value of the space should be 2,200. So you're over-ventilating to try to maintain 1,000 parts per million. So visually, this is what it looks like, just for adults that are seated in a space. You can see how the CO2 is different. If I make these adults and I have them walk around while they're working, then the ventilation rate to maintain 1,000 parts per million is much higher, or the same rate that we have per standard 62. This is another way to look at it. What I have done is I've compiled all the different metabolic rates on top of each other, so you can actually see how much it goes up. So if I take 1,000, and I'm looking at, for example, the last thing there is a fitness facility. It's almost 65 CFM per person to maintain 1,000 ppm in a fitness facility. So does that seem reasonable? That sounds like a lot of wasted energy, doesn't it? So I think they can probably get away with a higher CO2 value in there, and they do by the standard. But if someone says in their specification, you shall maintain 1,000 parts per million, and this is a fitness facility, and everybody's in there exercising, you're going to be wasting a lot of energy. Maybe the equipment, because the equipment was selected based on the design, based on standard 62, the equipment's not going to be able to keep up. You're going to oversaturate the coil. You're going to have a clammy space if it's in the eastern part of the country. So I decided to take a look to see what the internet would tell me about CO2. I did a Google image search, and I come up with all these different values. It's really surprising to see what's there. Should you avoid, if possible, if it's 800 to 1,000? How about this one? Nice smiley faces there. Here's one. Another interesting is a lot of CO2 sensors max out at 2,000. You have to make sure the CO2 sensor actually will go beyond that because, as I've already shown you, we have spaces that are going to be beyond 2,000. So if the CO2 sensor is maxed out, it's really not really going to help to do that. This one I like the best because it says that ASHRAE recommended level is 1,000 parts per million. And the only time that ASHRAE actually said that, again, is in the standard 1989. It was thus removed after 89, and in the later versions it said there was a differential number in there, and then that number was removed. And so this is not exactly correct. The internet doesn't always tell us the truth. In fact, I decided to ask ChatGPT before I came in here what the indoor air quality, what the indoor CO2 value should be. And it came back and basically said, you can try this yourself, between 400 and 1,000 parts per million. ASHRAE recommends that. Okay, ChatGPT. They must work for ASHRAE. I don't know. So here's a good example. This is something I found that actually was built a couple years ago in Houston, and we know the weather in Houston is just beautiful in the summertime, dry, cool. So they have this requirement that they had the new performing arts for this university. And the first thing I noticed here is a CO2 sensor in the space Well, as I mentioned before, just one CO2 sensor for this whole theater? I hope they have more than one. But the specification calls for a CO2 sensor. So what does the contractor do? Put a CO2 sensor. Where does he put it? I don't know. Here's another interesting thing. It says, when the CO2 value is below 800 ppm, go to the DCV minimum position, which is supposed to represent the ventilation rate for the unoccupied space, or the ventilation rate for the furniture, the chairs, the building itself. That's the minimum ventilation rate. But wait a minute, if it's 800 and outside is 420, that means there must be people in the space because it's higher than 420. So it's actually too low. And it says maintain 1,000. Well, if you remember the numbers I showed you before, 1,000 is kind of low for an auditorium. So something may happen. And this is the best part. Alarm, if it's over 1,100. Do you think it's going to be an alarm? Yes. Yes. What's going to happen to the alarm? They're just going to shut it off, right? Worst thing is if they actually try to control to this. So I decided to go through and calculate what the actual CO2 would be in this space, go through the math, find out what the actual ventilation rate per person is, 7 CFM per person. That doesn't sound like a lot, does it? If you think back earlier on, when I showed you the original formula that was saying 15 CFM a person was equal to 1,000 parts per million back in 1981, this is half of that. So it's very little ventilation, but this, again, is according to our standards. And so if you wanted to maintain 1,000 parts per million, you're 2.5 times what their minimum requirements are. You can do that, but you have to design for it. Because if you don't design for it, then you have a lot of ventilation air, and you're going to have a very clammy discharge air. You're not going to be able to maintain the space in the summer months in Houston. And you're going to waste energy doing that. So it's okay if you design it that way, but don't specify it should be maintained that way if you're not going to design it that way. And I'm pretty sure that they didn't design it this way because I looked at the coil load there and the number of people and everything lined up. This was to the code. So often I've seen factory-installed CO2 sensors. In the new addendum AB for 62, we're saying in the room, we're following what California Title 24 did. It makes sense in the room, in the breathing zone, definitely not in the unit. You can do one in the room, you can do one in the, I'd say do one in the room, do one in the duct, return duct, look at them both, see if they track each other, then you know if things are working. But this is what happens when you ask for a manufacturer to put it in. So this is an economizer, minimum outside air damper. You have your outside coming in through the blue, you have your return air coming in, and you got a CO2 sensor slapped on the side of the sheet metal of the damper with the holes sensing for the CO2 on the side. It's not looking at the return air, it's looking at the mixed air. So how is this going to work? It's going to be great for DCV. It's going to save lots of energy. It's not going to be so good for indoor air quality because it's never going to come off that minimum unless we go into economizing mode. So if you're in a mild climate where you're going to economize more often, then you're going to be okay. If you're in a climate like in Texas, then you're going to have a challenge maintaining indoor air quality, maintaining those ventilation rates. Another problem out there is what they call two-point control. And that's where they say, okay, let's maintain 1,000 parts per million and not do anything until we reach 1,000 parts per million. Well, that's not what you should do. Anytime you go above ambient, again, if ambient's 420 and the room is 500, that damper should already be creeping up. It should already be moving up. It should be proportionally moving up. That's the best we can do with CO2. We can't directly match it. We can only guess. We can proportionally integrate it between here's our span, our max ventilation rates, here's our CO2 range, and let's divide it by those two values. So if you look at a classroom that's fully occupied with 35 students, and you set it to 1,000, okay, this is what's going to happen. For the first half of the first period, the ventilation is going to stick at minimum because it's not going to reach. It takes, as I mentioned before, it takes a while to fill up the space, got to get that CO2 concentration up. Once it gets there, it's going to do a pretty good job because the classroom's going to continue. The kids are going to leave, come back in, kids are going to leave, and it's going to pretty much maintain that throughout the day if everything is set right to begin with and you can reach that value. This is another specification I found. It's pretty much similar except for it was for VAV and it used the value of 1,100 parts per million. But I just want to show an example of another classroom. So this is a high school classroom, maybe it's a middle school, maybe it's a university classroom, and you don't have the same class size in the same room. So it changes. You know, it goes from Spanish to math to something else, and so it's always changing the population. So what's going to happen if, in a two-point control, if you have a lower occupancy than what you designed for, if you design for 35 and you only have 10 kids in there, and you have your sequence set so that you're not going to operate until you reach that 35 level, then you're never going to move the damper. Again, very good for energy, very bad for indoor air quality. And this is done all the time. So eventually, it raises up when you get to 35, but then it drops back down, and pretty much you underventilate the whole day. The challenge is ASHRAE 62 is a minimum ventilation standard, and today we treat it as the maximum value. People are afraid to go above it. You know, as was said in the session before, you know, we have to balance energy and indoor air quality, energy and ventilation. It's not one or the other. We have to make sure that what is best for the client, what is best for the space. This one is not great, but it's better. It's a lot more layered. There's a lot more going on with this one. They're looking at the pressure in the space. As I said, you know, think you can have bad pressure in a space, and that's causing other problems, and they're operating the exhaust fan based on that pressure in the space. They're using airflow measuring station. They're using a CO2 sensor. They're looking at the actual flow rate. They're looking at the actual CO2, and they're using multiple values to come up with the right thing. It's not just one value they're looking at. They're looking at multiple things to control the indoor air quality. And so forth. So what I would recommend, you know, is let's measure the air, let's measure the CO2, look at it like a VAV box. You wouldn't run a VAV box and try to cool a space without sensing the temperature in the space. So why are you trying to ventilate a space without actually measuring the ventilation flow and using some other value like CO2? You can use them both. You should also be looking at VOCs. You should also be looking at particulate matter. But if you take this and you put it in the same sequence like a VAV box, reset it based on the CO2 value as the CO2 climbs, then it will work. Same thing happens. You have temperature in the space. You have a minimum VAV value. You have a maximum VAV value. As the temperature increases, you increase that VAV box opening to cool off or heat up the space. Or you can get a little more dynamic. You can try to solve for that outdoor CFM per person. You can try to figure out how many people in the space by calculating the number of people in the space. So you measure CFM, you measure CO2, you calculate the number of people based on the formula. Using the math I was showing before. Yes, this is a relationship between people. If you know what's happening in the space, it's not an easy thing. You have to know who's occupying the space. That's the challenge with CO2. That's what I'm trying to get across here. You know, if you don't know what's going on, it's a challenge exactly. But it's better off than that. Yeah, I think the best way is to actually count the people, not use CO2, right? So if you have a movie theater, don't use CO2. Because you have a point-of-sale system that's actually telling you how many people are seeing that movie today at what time. You have the point-of-sale system that can tell you there are 30 people in the theater, so let's ventilate for 30 people. Why are you using CO2? It's going to be halfway through the movie theater before the movie is done, before the CO2 builds up and you start opening up the outside air damper. There's many ways to do it. You can have occupancy counters on the door, so when people walk in, it counts the people. When they walk out, it subtracts the people. There's a new standard, there's a new guideline, Guideline 42. For ASHRAE, it's the guideline that was built on top of ASHRAE 62 for indoor air quality, and it discusses some of those techniques and how you can better do it. So that's a very good question, thanks. So There's this position document, as I mentioned, that came out last year. Dr. Pearsley was also involved. He was leading the team, and the position document was great, since he's the expert on that. I was just with him in Denver last week, or the week before. ASTM is also working on how to use CO2 to evaluate buildings. So we're working on that paper as well. So the position paper basically says, you know, CO2 doesn't necessarily indicate good indoor air quality. As I mentioned, there's many things that can happen in the space. CO2 is a marker of people. And we're trying to determine what the ventilation per people is. Okay, there have been studies that basically say, okay, high CO2 levels directly impede a person's ability to function well. We know over 5,000 parts per million, it can be detrimental to health if you stay in a space long enough. But at 2,000 parts per million, not really bad for the health. If it was, then we wouldn't have spaces that are ventilated to that level in ASHRAE 62. It could be that the result of these studies is because, well, a higher C2 means you have low ventilation. Lower ventilation, you're less alert. Higher ventilation, you're more alert. That's why they pump oxygen into casinos. That's why they ventilate a lot in casinos. They want people alert. They want people gambling. They don't want them to fade off. CO2 as a risk for airborne disease. There's no direct correlation between the viral load of an individual and the CO2 level that that individual is producing. It can be completely different. Certainly, someone that's singing is exerting more and producing more CO2, but they're also throwing a lot more virus out there as well, right? But it's not a direct correlation. It's an indication. So people are running around with CO2 sensors right now saying, "Oh, I'm going to get COVID because, you know, the CO2 is really high." It's possible. It may be true, maybe not true, but it's not a direct relationship. So be aware of that. And, you know, this is basically the tracer gas I'm talking about. This is basically how we use CO2 for DCV. Yes, if you know the value outside and you know the value that's being produced inside and you know what's leaving, then you can try to determine the ventilation rate. Again, saying that, hey, sensor accuracy, where it's located, this is all important stuff. And here's something that you know, people don't think about. There are new technologies coming out all the time. The last session that was in this room was talking about, let's take advantage of new technologies. Well, some of these newer technologies, they have changes to the air. They may absorb CO2. They may produce CO2. Just because they absorb CO2 doesn't mean the room is getting healthier. And if they absorb the CO2, then you just broke the relationship between CO2 and people and ventilation. So you can no longer use DCV. You can't do the math that you want to do to calculate the number of people. And the same thing if it's generating. There are some things that generate CO2 trying to clean the air or conglomerate particles and things like that. So if you generate the CO2, that also breaks the relationship between ventilation and CO2. And that is it. So just, the whole point was just be aware. It's not a solve-all.